YouTube started recommending these cool particle simulations such as Pez's work video, as well as Michael Richardson's on his 3D particle simulator, which led me to build my own. In this video, I'm first going to go through the process of how I made this 2D particle simulator, and then a quick overview of how I made a 3D version. Now the question is, where do I begin? Before we can get to the interesting particle physics, we need a canvas to draw on. For that, I'm using modern OpenGL to create a window. I'll be skipping the technical rendering details in this video to focus on the main simulation itself, but you can get an idea of it here. Now we can run it, and just like that, we have a nice window to work with. Next up is drawing the particles. To start, I define a struct that holds each particle's position and radius for now. Then I can write a function to give each particle a random position on the screen, along with functions that generate OpenGL vertices and draw the particles on the screen. Running this, we can see the circles on our screen representing particles. I can also change the particle size and run it again, and we can see that particle sizes have changed and they are in a new position. Now it's time to make them move, and for that we need a way to update their positions over time. I'll be using a method called Verlet integration. It's commonly used in physics simulations because it's simple, stable, and doesn't require us to keep track of velocity directly. Most physics classes start with this familiar kinematic equation, but Verlet takes a different approach. Instead of velocity, it uses current and previous positions, along with the acceleration to compute the next position. You can think of it as kind of a prediction. It takes the current position, adds displacement from the previous step to see where the particle is heading, and then nudges it with a correction based on its current acceleration. To implement this, I started by extending the particle struct to include previous position and acceleration for both axes, plus mass for future use. I then wrote a Verlet integration function based on the equation we just looked at. In the main loop, I set the time step and gravity, ran the Verlet update for each particle, and advanced the simulation time. Now you can see that when we run this, we now have falling particles due to gravity. However, we run into our first problem. When we run, our particles go off the screen. To fix this, we need to add boundary collision detection and correction. To detect a collision on the bottom, for example, we would check if the position in the y direction minus the radius is less than the y position of the boundary. In other words, has the particle crossed the bottom boundary? If it has, we can estimate the velocity based on the difference between the current position and the previous, and use it to reverse the velocity by adding the difference between them to the current position. In between, we can also snap the particle back to the boundary. You can also see that we repeat a similar process for the top, left, and right boundaries. Now when we run it, we have particles bouncing off the bottom. We can also check the sides by adding gravity in the x direction and running, and see that this works as well. They bounce off the sides. Next, we need to add collisions between the particles, which involves detecting these collisions and resolving them. The simplest way to do this is brute force method. We can check for collisions by looking at a particle and going through all other particles to determine if they collide with it. If they do collide, we can resolve the collision using basic physics principles. To resolve a collision between two particles, we estimate their velocities using their current and previous positions as required by Verlet integration. We then compute the vector between their centers to get the collision normal and check if they overlap. If so, we apply a position correction along the normal scaled by the relative masses to separate them. Next, we calculate the relative velocity and project it onto the normal. If they are moving toward each other, we apply an impulse scaled by the coefficient of restitution to simulate the bounce. Finally, we update each particle's previous position using the new velocity, ensuring proper integration the next step. Running this simulation shows that we can now see particles colliding with each other. However, if we increase the number of particles, we can see that the simulation slows down dramatically due to our brute force method for collision detection. This slowdown is due to the fact that when we check if a particle is colliding, we check it against all other particles. The better method we can use is a spatial grid collision check, where we first begin by splitting up the domain into a grid. We can then create a neighborhood of 9 cells where we check the particle against all other particles in this neighborhood to see if they're colliding. After implementing this method, we can run the code and see the improvement. Now, instead of the particles just falling onto the boundary of the window, I decided to add a circle for the particles to bounce in, which required new boundary collision checks. I also added a way to pull the particles and push them away from the mouse. We can try this out. Lastly, I wanted a couple ways to spawn particles throughout the simulation, as well as have the particles change colors based on speed. Here's the final version of the 2D particle simulator. Now that the 2D simulation looks decent and is working, I will begin the process of making the 3D solver, while skipping the code since most of the major changes were rendering, and the physics side was mainly just adding a third dimension. To begin, we first need to make something for our particles to interact with, and since we are in 3D now, I made a wireframe sphere. Next, we need to add some particles. And then we need to make them fall due to gravity. Then we can make them bounce off the wireframe sphere. However, the particles are not colliding with each other. We need to add the grid collision, and now we have particle collisions. Lastly, I add color mapping based on speed as well as mouse interaction, just like the 2D solver. Now we can mess around with it. I think I'm going to finish the video here. If you made it this far, thank you for watching. Also, if you have anything you would like to see me add to this or anything you would like to watch a video on, please leave a comment below.